The jungle breathes a respiration of vapor and decay that hangs heavy in the lungs of the Annamese Cordillera. In this hyper-humid terrain, where the air moisture content hovers near saturation, the primary threat to a lacerated human body is not merely blood loss but the environment itself. A wound left open in the Vietnamese tropics does not scab, it weeps. The ambient humidity inhibits the evaporative phase of coagulation, leaving the tissue vulnerable to the colonization of Pseudomonas and fungal spores that thrive in the heat. 700 years ago, a soldier navigating this greenhouse sustained a deep laceration from a bamboo punji stake or a slip against serrated rock. He did not reach for cotton or linen, materials that rot and foster anaerobic bacteria in this climate. Instead, he looked to the canopy for the golden gleam of the Nephi-la-Pili-Ps. He gathered the thick, sticky web of the giant wood spider, balling the protein strands into a dense mass, and packed it directly into the open meat of his leg. This was not superstition. It was a calculated application of bioengineering. The web acted as a hydrophobic mechanical seal, allowing the wound to breathe while repelling the ambient moisture, its fibers activating the body's clotting factors through surface contact chemistry. The bleeding stopped. The rot was held at bay. This survival protocol, born of necessity in the ancient Indo-Chinese jungle, predated modern regenerative medicine by centuries, relying on a material that remains one of the most sophisticated polymers on Earth. The historical utilization of arachnid silk in Vietnam, distinct from the Greco-Roman traditions of Europe, was driven by the specific exigencies of the tropical climate. The 14th century physician monk Tu Tin, in his seminal Pharmacopoeia Mduka than Huo, codified the use of local fauna to treat indigenous ailments, establishing a medical philosophy that prioritized the immediate availability of biological resources. In this context, the triduvong, the spider web, was not a generic material, but a specific tool selected for its chemical and physical properties. The web of the Nephi-la-Pili-Ps, known locally as the Na Chen Rong or forest spider, was favored for its immense tensile strength and volume. These webs, often spanning to meters across the canopy, provided enough material to create a substantial hemostatic plug for arterial hemorrhages. Unlike the white silk of common house spiders, the Nephi-la silk is gold, pigmented with xanthurenic acid, a chemical variance that signals a different molecular composition. When applied to a wound, the high surface area of the nanophyzers, some as thin as 0.01 micrometers, triggers the intrinsic pathway of the coagulation cascade. The negatively charged surface of the SB-IDRON proteins acts as a catalyst for factor XII, the Hageman factor, initiating the enzymatic chain reaction that converts prothform into thrombinin, ultimately soluble fibrinogen into the insoluble fibrin mesh that constitutes a blood clot. The efficacy of this primitive dressing extended beyond simple mechanics. The silk of jungle-dwelling spiders is coated in a hygroscopic calaceous layer containing chelini, betaine, and isethionic acid. In the wild, this coating prevents the web from becoming brittle in the sun and protects the protein from fungal degradation. In a human wound, these same compounds create an antimicrobial and antifungal shield, essential in an environment where mold can colonize exposed tissue within hours. Furthermore, the silk is rich in vitamin K, a critical cofactor for the synthesis of clotting factors II, VI, IX, and X. By packing a wound with fresh web, the ancient practitioner was essentially administering a topical infusion of coagulants while simultaneously creating a breathable, antibiotic barrier. The Namduka tradition recognized the web as having a salty taste and neutral nature, classifications that aligned with its observed ability to cool the blood and reduce the toxicity of inflammation. The biological machinery responsible for this material is a marvel of evolutionary specialization. The Nephi-la-Pili-Ps exhibits extreme sexual dimorphism, a phenomenon known as female gigantism and male dwarfism. The female, the primary silk producer, is a massive biological factory with a body length of up to 50 millimeters, while the male is a fraction of that size, often measuring only 4 to 6 millimeters. This disparity is driven by fecundity selection. The female requires immense metabolic resources to produce eggs in the vast quantities of silk necessary for her webs and egg sacs. Her silk glands secrete SPIDROINs, large repetitive proteins that transition from a liquid crystal-lined OP into solid fibers, as they are pulled through the spinner ETS under shear stress. The resulting fiber is a composite of crystalline nanoassemblies, formed by polyalanine beta sheets that provide steel-like tensile strength, and amorphous glycine-rich domains that grant rubber-like elasticity. This combination allows the web to absorb the kinetic energy of a flying insector, the hydraulic pressure of a bleeding wound without fracturing. Beyond the canopy, the ethnomedicinal practices of the region utilized other arachnids for specific pathologies. The heteropod A. venatoria, or brown huntsman, does not build a web, but hunts on foot. Its utility in medicine lay in its shed exoskeleton, the Tridae. In the Char-Chap Ori communities of Assam and the villages of Vietnam, this chitinous debris was collected, charred, and ground into a paste to treat menorrhagia, the condition of excessive menstrual bleeding. The mechanism here likely involves the adsorptive properties of the carbonized chit in unresidual surface peptides, which may possess vasoconstrictive properties similar to those found in the venom of related species. The egg cases of the Urocti compactile is known as bitched yen, or similarly roasted and used to treat abscesses and throat infections. The roasting process, or saut untin, denatured the proteins while preserving the mineral structure, creating a primitive activated carbon sponge capable of drawing purulent exudate from infected tissues. Modern material science has spent decades attempting to reverse engineer the jungle bandage. The primary obstacle to industrializing spider silk is the arachnid's predatory nature, and like silkworms, spiders are cannibalistic and cannot be farmed in high-density colonies. To bypass this biological constraint, researchers have turned to transgenic synthesis, inserting spider silk genes into organisms ranging from E. coli bacteria to goats. In Utah, transgenic goats lactate milk containing dissolved spider silk proteins, which are then purified and spun into fibers. In laboratories, bacteria are fermented in bioreactors to produce SPIDRO and O. These synthetic analogues aim to replicate the hierarchical structure that gives the natural fiber its medical utility. The translation of these proteins into clinical products involves advanced processing techniques such as electrospinning. By dissolving purified silk proteins in solvents like hexafluoropropanol and subjecting them to a high-voltage field, scientists can produce nanofibers with diameters as small as 417 nanometers. When combined with biodegradable polymers like poly-L-lactic acid PLLA, these nanofibers form a scaffold that mimics the extracellular matrix of human skin. The results of preclinical trials using these materials validate the observations of the ancient Vietnamese healers. In rat models with full-thickness skin defects, PLLA spider silk dressings demonstrated a % improvement in healing rates compared to control groups. More significantly, the silk scaffolds actively promoted angiogenesis, the formation of new blood vessels. The presence of silk proteins resulted in a 16.3% increase in blood vessel count and a staggering 118.6% increase in vascular branching. This pro-angiogenic effect ensures that the regenerating tissue receives adequate oxygen and nutrients, preventing the necrosis and scarring that often plague deep wounds. The integration of spider silk into wound care has evolved into the development of smart dressings. Utilizing click chemistry, researchers can covalently bond antibiotic molecules, such as levofloxacins, directly to the silk fibers. These antibiotics remain inert until the dressing comes into contact with bacterial enzymes in the wound bed, which cleave the bonds and release the drug locally. This targeted delivery system maintains a high concentration of antibiotics at the infection site while minimizing systemic side effects. Furthermore, the development of laser-activated silk elastic cell (ESS) represents a fusion of ancient material and photonic technology. These silk-based sealants, doped with gold nanorods or dyes, can be applied to a wound and activated by a near-infrared laser. The laser energy is converted to heat, bonding the silk protein to the tissue and creating an instant, sutureless seal that possesses biomechanical strength superior to traditional stitches. The comparison between spider silk and conventional medical treatments reveals the limitations of synthetic chemistry. In controlled studies, spider silk-treated wounds healed significantly faster than those treated with povidone-iodine or standard tetracycline ointments. While povidone-iodine is a potent antiseptic, it is also stichotoxic to fibroblasts and keratinocytes, often delaying the reepithelialization process. Spider silk, by contrast, enhances the proliferation of these cells. In experiments involving P. holcus phalangioite silk, wounds closed completely in 14 days, compared to over 20 days for untreated wounds and 18 days for those treated with standard antiseptics. The silk acts not just as a cover, but as a biotic scaffold that guides the migration of cells across the wound bed, reducing the time required for epithelial closure and minimizing the deposition of disorganized collagen that leads to scarring. Yet the raw application of spider webs is not without peril, a reality that necessitates the rigorous purification protocols of modern medicine. A web in the wild is a passive filter for the jungle's atmosphere, collecting pollen, dust, and necrotic debris. The introduction of a raw web into a deep wound carries the risk of secondary infection from pathogens like Clostridium tetani. Ancient practitioners mitigated this by selecting webs from sheltered locations or treating them with wine and vinegar, but the risk remained. Additionally, the misidentification of species in the biodiversity of the Mekong region could lead to the application of silk containing urtica hairs or neurotoxis residue. The venom of related species contains toxins that block voltage-gated potassium channels and induce systemic paralysis, a catastrophic complication for a wounded individual. Modern recombinant silk eliminates these variables, providing a sterile, consistent protein structure free from environmental contaminants and immunogenic arachnids. The trajectory of this material from the damp, mosquito-choked jungles of 14th century Vietnam to the sterile, laser-equipped operating theaters of the 21st century illustrates a continuity of human ingenuity in the face of physiological trauma. The fundamental problem how to seal a breach in the body's integrity while promoting regeneration remains unchanged. The solution, refined by millions of years of evolutionary pressure in the spinner, ETS of the Nephi law, remains superior to many synthetic alternatives. We have dissected the protein, sequenced the gene, and spliced it into bacteria and goats, yet we are essentially attempting to replicate the same tri-duvong that a desperate soldier once pulled from the trees. The technology has changed, but the architecture of survival is ancient, woven into the very fabric of the natural world, waiting to be harvested by those who know where to look.